This video will delve into the concept of acceleration. Let's first begin with a thought experiment. Imagine that you are in an insulated car. You cannot feel vibrations, you can't hear any noise, and the windows are blackened. You take a nap and you wake up from your nap and you're trying to figure out whether or not the car is actually moving. In which situations would you know that the car was moving, and in which situations would you be unsure whether or not the car was moving? Pause this right now and write down in your notes your thoughts. So when would you know that the vehicle was moving? There are essentially three situations. One, if you were speeding up, two, if you were slowing down, and three, if you were turning. In all three of these cases, it's an acceleration. Let's define acceleration. Average acceleration is equal to the change in velocity over change in time. Note, this can be because of a change in speed or a change in direction. Here is the equation. A is delta V over delta t. This is a note card equation. You should write it down. Note, acceleration is a vector because change in velocity is a vector. Note, the units of acceleration can take many forms. Miles per hour per second, feet per second per year, meters per second is what we'll be using most commonly. Pause the video and complete this follow-up question. Name three controls on a vehicle which provide acceleration to a car. Let's start by doing a simple example. A car starts at rest and accelerates to a velocity of 10 meters per second north in 5 seconds. Find the average acceleration. So we'll start by writing down our given information. Initial velocity is 0. Final velocity is 10 meters per second north. The time is 5 seconds, and we're looking for the average acceleration. So we know by definition that our average acceleration is the change in velocity over change in time, or v final minus v initial over t. Now we're going to define the positive direction to be north, so we just have the final velocity is plus 10 meters per second minus 0 over 5 seconds. So we get plus 2 meters per second, or plus 2 meters, no plus, 2 meters per second squared north. Now if we think about what this plus 2 meters per second means that the velocity is changing by plus 2 meters per second every second that passes. So if it starts at rest, its initial velocity is 0. After 1 second it'd be going 2 meters per second. After 2 seconds, 4 meters per second. After 3 seconds, 6 meters per second, etc. So we get our final answer is 2 meters per second squared north. Okay, let's do another example. In this situation, a car is initially moving 10 meters per second north and slows down to 2 meters per second in 2 seconds. Find the average acceleration. Again, we're going to define the positive direction to be north. So let's get my pen. Our initial velocity is 10 meters per second. Our final velocity is 2 meters per second, and our time is 2 seconds. Our average acceleration is delta V over delta t, which is equal to 2 meters per second, the final velocity, minus the initial 10 meters per second, all over 2 seconds. So in the end, we get a value of negative 4 meters per second squared. Now remember, we defined the positive direction to be north, so when we have a negative 4 meters per second squared, that is also the same as saying 4 meters per second squared south. Let's now do a third example. Now we have a car that is initially moving plus 15 meters per second and has an acceleration of negative 5 meters per second squared. Pause the video and fill out the table for the velocity over a 6-second time period. So here is the table filled out. The velocity starts at plus 15, goes to plus 10, plus 5, 0, negative 5, negative 10, and negative 15 meters per second, following the acceleration of negative 5 meters per second, meaning the velocity changes by negative 5 meters per second every second that passes. Now I do this example because I want you to note the difference between the first 3 seconds and the second 3 seconds. In the first 3 seconds, it is moving in the positive direction and it is slowing down as time passes. It then comes to a rest at time t equals 3 seconds and then continues with an acceleration of -5 meters per second such that it starts moving in the negative direction and speeding up. So we cannot think about a negative acceleration as meaning that an object will be slowing down. The negative just tells us a direction of the acceleration. We need to consider how the velocity and the acceleration directions compare to determine whether an object is going to slow down or speed up. Please complete follow-up questions 2 through 6 by watching the following 5 videos. For each video, state whether the acceleration is positive or negative. Note that positive direction is to the right. Now complete the following questions using the tables shown below. In this video, we investigated the concept of acceleration. We determined that acceleration was a change in velocity over time, which could happen from either a change in speed or a change in direction. We will learn about the change in direction piece later. Also, we concluded that a negative acceleration doesn't always mean an object slowing down.